This video will highlight the genius of the great Gottfried Wilhelm von Leibniz, the most intelligent person who ever lived. His contributions in mathematics, philosophy, physics, computer science, and other fields were unmatched. These contributions earned him the nickname, the last universal genius. He developed a calculating machine that he designed himself and introduced the binary number system and binary arithmetic, which is the language used by all the computers and gadgets we use today. But his most important achievement, perhaps his most famous one, is his discovery of the most difficult branch of mathematics, the calculus. Leibniz's discovery of calculus in 1674 occurred while he was trying to determine the area under the curve. In a Cartesian coordinate plane, Leibniz observed that the number of triangles underneath the graph increases as the x and y values increase. When the x and y are 1, the number of triangles is 1. When x and y are 2, the number of triangles is 4. When x and y are 3, the number of triangles is 9. When x and y are 4, the number of triangles is 16. Leibniz wrote down a function that best describes this pattern, which is number of triangles equal to w squared, because plugging in the values will give us the same result. But there's a problem with the function, as it only displays the number of triangles, not the actual area. In Euclidean geometry, if a triangle has a base and a height of 1, it will have an area of 0.5. A triangle with a base and a height of 2 produces 2. A triangle that has a base and height of 3 yields 4.5, while a triangle with a base and height of 4 yields an area of 8. Comparing the results shows that Euclid's formula for triangles produced different results from Leibniz. So Leibniz experimented with a different approach by increasing the exponent of x by 1 in the curve or line function y equals x, and then dividing the term by the same exponent, transforming the curve or line function into an area function. Plugging in the values obtained similar results as Euclid's method. Leibniz tried a different function to test the effectiveness of his method, the curve function y equals x squared. He incremented the exponent of x by 1 and divided x by the same exponent to convert it into an area function. The results when values are plugged in give the area under the curve. He also tried the same method for the curve function y equals x cubed. Using the same method, accurately it calculates the area under the curve. Leibniz was convinced that the method is effective and was amazed by this breakthrough in mathematics. He called the method of finding the area under the curve integral calculus. The inverse method of integral calculus is differential calculus. In contrast to the method of finding the area under the curve, differential calculus aids in determining the curve above an area. Differential calculus provides information about the shape of the graph and its direction of movement. Let's take our previous example, the area function a equals x squared over 2, and reverse the method by multiplying x by the same exponent and decrementing the exponent by 1. Simplifying brings us back to the curve or line function we had before. This also applies to the area function a equals x cubed over 3. Reversing the method will give us the curve function y equals x squared. The area function a equals x raised to the power of 4 over 4 when x is multiplied by the same exponent, and decrementing the exponent of x by 1 will bring us back to the original curve function y equals x cubed. To sum up, integral calculus is a technique for determining the area under a curve or line by converting a curve or line function into an area function. To illustrate, the curve or line function of this circle is y equals 2 pi x. This function provides information about the circumference of the circle, not its area. It is only when we perform integration that we are able to generate an area function that helps us determine the area of the circle. On the flip side, differential calculus is the complete opposite of integral calculus. This tool allows us to determine the curve or line above an area. Using differential calculus, we can convert an area function into a curve or line function. For example, this area of the circle with the area function a equals pi x squared. This function provides us with information on the circle's area. Using the differentiation method will enable us to generate a curve or line function that helps us determine the circumference of the circle.